So this is a demonstration I've been planning for a while, but I needed to have two equatorial mounts before I could do it properly. The mount on the left is the Celestron AVX, which I purchased several months ago, and the one on the right is a Skywatcher as EQ6, which I purchased last week. Now, they are both German equatorial mounts, and on the wall behind you can see I've just put a little marker indicating the direction of north. Now, I've set up both of these mounts for respective locations in the southern hemisphere and the northern hemisphere. On the left, it's set up for Sydney, Australia, 34 south latitude, and on the right, it's set up for Los Angeles, USA, which is approximately the same latitude but to the north, 34 north latitude. So what you can see is the telescope on the left is pointing south. It's actually pointing at the south celestial pole. The telescope on the right is pointing towards Polaris, if it was aligned like this in Los Angeles, California. Now I'm going to just move closer to the mounts and just talk a bit more about this polar axis alignment and why they look so different when we're looking at them like this. So firstly, in Sydney, Australia, we've got this AVX mount, and the polar axis is this axis through here. Okay, so this is actually aligned to 34 degrees up from level. Okay, and it's facing south, so the higher end of the axis is facing south, which means technically pointing down in this direction, it's pointing towards Polaris, because we can't see Polaris from Sydney, Australia. It's completely below the horizon, and it never rises above the horizon. We're at 34 south latitude, we never see Polaris. For the other telescope, which is aligned for the northern hemisphere, okay, you will see that it's aligned this way. This is the polar axis, and the southern end is now pointing downwards and the northern end is pointing upwards. So that would actually be pointing up towards Polaris. Now you can see there's an obvious difference there, isn't there? Okay, one is pointing downwards towards Polaris, the other one is pointing upwards towards Polaris. So obviously that's just not going to work, and yet these are correctly aligned for their respective locations. So let's just explore that a little more. So just looking at this polar alignment, this Skywatcher mount actually incorporates a dedicated polar alignment telescope. It's a small telescope that runs straight up the middle of the polar axis, and by just removing that plastic cap you can see out the other end. Now when you are setting up this telescope in the northern hemisphere, we would align that with Polaris. Now, not precisely on Polaris, there's actually a small reticle on the display of the telescope that shows you precisely where to position Polaris to get that perfect polar alignment. When you're doing that, you're actually aligning this polar axis, the rotational axis, with the true rotational axis of the Earth. And similarly with the AVX mount, this does not come with a polar alignment telescope, but I can remove that cap. And again, it's got the front cap you can remove, and it's an option on this mount. Basically, you can put the polar alignment scope in there. There are other ways to do a polar alignment, which I've basically used, and certainly even with this scope, I can't see Polaris from Sydney, so I have to use different techniques to get an accurate polar alignment. But what you can see, again, really emphasizing this point, is that the polar axis, the polar alignment axis, is pointing down towards the south. Remember, north is to the right as we're looking at it. It's pointing up towards the north, down towards the south, as it would appear in Los Angeles, USA. In Sydney, at an equivalent southern latitude, it's pointing the opposite direction. It's pointing upwards towards the south and downwards towards the north. So we're just going to have a look at that geometry, and I'll show you a short graphic showing the reticle in this polar alignment scope. So I'll just demonstrate this polar alignment scope. I've just turned up the LED. It is actually illuminated. Now it might just be a bit difficult to align, so just bear with me, but I will try to show you. Okay, so there's what you will see through the polar alignment scope, and over here it's going to show you where to put Polaris when you're aligning the scope. Now you can see there are different dates there, and then if you're in the southern hemisphere, it's showing you which stars you need to align to give you that correct polar alignment. Now let me just show you that on a laptop as well. So this is what we were looking at in the polar alignment scope. It's the engraving that shows you precisely where to put Polaris when you're aligning the scope. Now if you look closely, you'll see the position changes over time, and it's also not located directly at the North Celestial Pole. It's also set up with engravings for the Southern Hemisphere. There's a star pattern, and those are the stars you would align if you were doing a polar alignment in the Southern Hemisphere. So that's how we actually set up these telescopes, and once they're set up, they are perfectly aligned with the rotational axis of the Earth. So what I've done here is just orientate the telescope on the left to be pointing towards Polaris. So in Sydney, Australia, with this telescope set up like this, correctly polar aligned for my latitude, this telescope is now pointing towards Polaris. In the Northern Hemisphere, 34 north latitude, this telescope is also pointing towards Polaris. Can you see the discrepancy? How is that possibly going to work on a flat Earth? It simply won't. Now the reality is, these telescopes have their polar axis aligned exactly with each other. We're not seeing that in this demonstration because I have both telescopes, the tripods, mounted on the same flat piece of ground. But in reality, because of the curvature of the Earth, the orientation of the mounts is significantly different. There's 34 degrees north latitude, 34 degrees south latitude. That's 68 degrees difference. Okay, so there's actually a 68 degree difference between this polar axis and this polar axis. And if we were to align the mounts correctly, if I were to take this telescope on the left and tilt it 68 degrees that way, the small telescope would be pointing in precisely the same direction as the large telescope. So we can see quite clearly that the German equatorial mount design, when correctly polar aligned, is absolute proof that the Earth is not flat. They simply will not work on a flat Earth. They have to be aligned with each other. This rotational polar axis, in reality, they are the same angle. We're not seeing that because we've got both set up on a flat surface. So just to summarize once again, these telescopes are set up. The one on the right is set up for Los Angeles, California, USA, with the polar axis pointing upwards at 34 degrees to the north. The telescope on the left is aligned for Sydney, Australia, with the polar axis pointing up 34 degrees to the south. Okay, you can see there is a 68 degree discrepancy between the two axes. In reality, if these were set up at their respective locations, the true alignment of each axis would be equal. There would be a 68 degree difference in the level surface of the Earth between those two locations, and when those mounts are aligned and positioned on the Earth at the correct locations, the polar axes will be aligned. Now, the German equatorial mount works by rotating that axis in an opposite direction to the Earth's rotation. So when the telescope is pointing at an object in the sky and the mount is rotating opposite to the Earth's rotation, it's going to remain fixed. And that's how we can track objects across the sky from the moment they rise right through the meridian until when they set, just using a single axis of rotation on these German equatorial mounts. So there's a number of proofs here that we have. We are able to track objects across the sky with a single axis of rotation. The alignment of the polar axis confirms that the Earth is not flat because they are different. For the Northern Hemisphere and the Southern Hemisphere, they're quite different. Both of those telescopes are looking at Polaris. It doesn't work on a flat Earth. On a curved Earth, with 68 degrees difference between the two telescopes in the level of the ground, it works perfectly. The axes are aligned perfectly. So let's take a look at it on the globe. Now remember, those polar axes are not aligned with each other when the telescopes are set up on a flat surface. So if the Earth was flat, these mounts are just not going to work. And that's really the truth. They just will not work on a flat Earth. And yet, just with a bit of research and just going out and spending a few $100s and buying one yourself, you can confirm that they actually do work when you set it up correctly for your own latitude. Now let's have a look at why the mounts actually work on the globe. Because at Sydney, we are 34 degrees south latitude. So there's the equator. Now if we come down to Sydney, you will see if I put a line level with the ground at Sydney, it's 34 degrees. Now let me just rotate the globe and we'll have a look at Los Angeles, California. So now looking at Los Angeles, California, that is the level. So again, it's another 34 degrees. So looking at Los Angeles, California to Sydney, Australia, there's your 68-degree difference in the ground level. And when we were aligning these telescopes for the relevant locations, that ground level is actually not flat and equal at both locations. It's different by 68 degrees. And because it's different by 68 degrees, the polar axes of both telescopes will, in fact, be aligned. So that's why they're working in both locations. It's a polar alignment, which means it is aligning that axis with the rotational axis of the Earth. That's how these German equatorial mounts work. They absolutely do work. They could not work if the Earth was flat. And just to help you visualize it better, there's a telescope polar aligned for the southern hemisphere, and you can see again that polar alignment axis is angled down towards the north. Okay, that's exactly what we're seeing on my telescope that is set up for Sydney, Australia. There's the north to the right of the screen, and the mount is angled downwards towards the north, exactly as you would see it on a globe when it was polar aligned. So once again, as always, I really don't want you to just take my word for it. I just hope I can encourage you, if you're seeking the truth, to research this topic yourself. And it's as easy as typing in polar alignment into Google, looking at the images and watching a few videos, and you will see the geometry of how these equatorial mounts work and how they're aligned. And there are literally thousands of images, and you can even buy an app for your phone that helps you polar align it correctly. Now, if you go to the videos, there is a huge resource of information. You know, people are showing you how they polar align their scopes, different brands for the northern hemisphere, and you know how to polar align a telescope in the southern hemisphere. So when you're doing your research, hopefully that's going to help you very clearly understand the true shape of the Earth, because equatorial mounts give us absolute proof that the Earth cannot be flat, because they simply would not work. So the final thing I have to say about this is that I bought both of these telescope mounts from a telescope store in Sydney. Now, if the Earth was actually flat, you wouldn't find these mounts in a telescope shop. You'd find them in a boating shop, because if the Earth is flat, they're absolutely useless for anything except perhaps being an anchor